Okay, so good morning everyone. Today we're gonna start lecture 2, and I'm trying to use this, which is different from previous lecture. So let's see how it goes. Any questions about last week's lecture? I mean, couple of quick announcements. One is that I think I've uploaded assignment 1. Have a look at it. Basically, the questions are from one of the textbooks. I think one of the questions is from one textbook, and the remaining questions are from the other. So they will require you to start using R, and they will probably just quiz, just explore the concepts of k nearest neighbors and linear models. Basically, something called simple regression and multiple regression. Simple regression just means your input variable is just one dimensional, so 1 versus 1, and then multiple regression implies having multiple input variables. So like last time we had this dimension 3, right? So p is equal to 3, so that would be multiple regression. Okay. So today actually we're gonna really introduce statistics and probability into the mix. So I'll try to briefly recap some essential definitions, but this is something I think I posted a review on probability. How many of you had a chance to look at that PDF? Okay. How many of you felt that it was too difficult? Okay. So you want to ask questions on Slack so that other people can answer, right? So hopefully you can kind of get familiarized with the terminology, the language, and the concepts there. Actually, probability and statistics, is not really absolute truth. So the world doesn't really, sample things. Maybe if you flip a coin, you'll say it randomly comes out as a heads or a tails. That's, the randomness is because we abstracted out the physics of the process. So given the initial conditions and the amount of force that you applied, the number of rotations that the coin takes, and revolutions, rotations across some axis and falls as something, it's actually governed by the laws of physics, right? Newton's laws. But then we say it's random, so the outcome is random. So I guess what I'm trying to say before, and this is a point that you may forget at some point of time, is that the language of probability and statistics is just for our convenience. It's a model. Just like real numbers are not real. Okay, it's just something philosophical, I guess. This is a model to describe how the world behaves. Okay, and so you don't have to be extremely wedded to the notions of statistics and probability in general. But in this course, we'll try to use statistics as a way to kind of reason about data, okay, and real life phenomena. Okay, so today's lecture, let me just write down the goals. 4 points, okay. First I'm going to describe something called statistical decision theory. It's really not a theory or, not too much about decisions. It's just a language that we'll use, and we'll actually recognize a couple of key ingredients. It's called the regression function, and the second one is a Bayes classifier. Okay. So last time I tried not to use this word regression function because it's, statisticians have used this word for something specific, and we'll see what that specific object or quantity is. Okay, so these are the two concepts that we'll try to kind of figure out. These, in some sense, are the best regression, regression models are the best classification models. Okay. Then we'll go into, curves of dimensionality. Basically is trying to reason why KNN is not good enough. So last time I just said, just use KNN, right? But I didn't really back my backup, why you should use KNN. And in fact, last time I was saying that if you had small data, in the sense a less number of input variables and lots of observations, then KNN is good enough. So today we'll see why it may not be, why it may have some shortcomings if data is not, you're not in a small data regime. Okay. Third part is, so relation to the principle of maximum likelihood. I mean, I just call it supervised learning in the notes, but it's basically trying to say, connect. If you remember from last lecture, we had this residual sum of squares or some notion of a loss function. So we're going to relate it to a more general way of thinking about loss functions. Okay, that's the third part. And fourth part, again, we're going to look at linear models. Specifically, we'll attempt to derive that closed form expression that we had. I don't know if you remember that there was a beta hat is equal to X matrix transpose X matrix inverse X matrix transpose I guess Y vector. Okay, in if output variable is one dimensional. Okay, so let's start with the first part. Any questions at this point? Yeah. Yeah. So the the linear model that we looked at last time is actually not a classification technique, as in it doesn't output a classifier. It outputs I guess a regression model. Yeah, a regression model. So you can use a regression model for classification. Last time actually we did that somehow. We didn't explicitly say that, but we built a regression model and then said the regression model, and we defined when the regression model is equal to some constant value, like a 0.5 threshold for one dimension, or in two dimension also it was 0.5 threshold. That gave us a decision boundary which was linear. Okay, so the decision boundary has nothing to do with. So the decision boundary is different from the regression function. The regression function was a plane in two dimensions. The plane intersect threshold. I mean, the plane. You picked a particular line on the plane, and that's why the decision boundary was linear. Okay. Maybe I'll repeat the same thing again when I talk about, maybe in the fourth part. Okay. Any other questions? Yeah.
Driving this fourth function today?
Yeah, it's not difficult. I mean, it's we just need to know the differentiation. The derivative of a squared, x squared with respect to x. It's 2x basically. So that's basically the biggest part there. Yeah. Okay. So last time x was an input variable and y was an output variable. Just notice the difference between, here I've put a bar there, right? So this is the matrix. If you remember, x bar was n times p matrix. X was p-dimensional. And y, we can just let's say it's one-dimensional. Okay. If it's more than one dimension, for at least linear models, there's really not much change in picture. But so let's not worry about that. And y was n times one-dimensional. Okay. Now I'm gonna say let x be a random vector, a random variable, and let y also be a random, in this case let's call it variable, okay. Okay, and so if things are random variables, then they are associated with something called a density function or a probability mass function. So these are things that you should have looked at the review, but it's basically let's pick y because it's a simpler. It's just one dimension. So y can be distributed according to some density function. So let me just use the should I introduce a notation? Okay, p subscript y. I'm just going to use this to represent the density function. Okay. Okay, need not be density function, but okay. Either the density function or the probability mass function. So what's the difference between those two? Let's say y takes discrete values, as in let's say, so this is just an example. Let's say y only takes values. So this is how I'll represent. Y takes values between, let's say y takes values 0, 1 and 2. Okay. Then p of y can be described as basically the description is going to be p of y is just going to be probability that y is equal to 0 will be some number. I guess I should p of y is equal to 1 is some number, and p of y is equal to 2 is some number. Okay, and these three numbers add up to 1. Okay, that's a very simple definition for a random variable. So for example, here I can fill 0.1, 0.3, and what's the last one? Yeah, 0.6, because they need to add up to 1. So for some of you it may be too elementary, but for some of you, if you haven't seen this is just something you need to internalize, because we'll discuss some properties of these things. Okay, and if it is not discrete, that example you've seen. So let's say y is people write n, let's say n 0, 1. Okay, this is just to say that y is Gaussian or normally distributed. Okay, and all this means is that p of y is equal. P of y takes a value little y. Value this realization, remember, or observation is equal to, in this case, 1 by 2 pi. Okay, let me write the general expression itself. With some mean mu and variance sigma square, it's going to be square root 2 pi sigma e to the power minus y minus mu square divided by 2 sigma square. Okay, it has some weird expression, but all I'm saying is for every value of y from so this means that y can actually go from so this is an expression to say belongs to. Okay, it's just saying that for every value of y from minus infinity to infinity, I can evaluate this, and this is the probability that capital Y, the random variable, takes the value little y. Okay, this is just an example of a normally distributed random variable. So if y is one-dimensional, normally distributed random variable, then the probability that it takes a value little y is given by this weird expression. Okay. And even this, so with this you can't really sum finite number of things, because y is really taking an infinite number of values. Okay, minus infinity to infinity is actually uncountably infinite. Doesn't matter. But what I'm saying is here you have to think of integration. Okay, integration of this thing from minus infinity to infinity should be equal to 1. Okay. Yeah.
Is that just a delta symbol? It's in 2 pi.
Sorry, it's sigma. This thing.
Oh.
I mean, I'm using these notation because you'll probably see this notation in textbooks, so it should not be too unfamiliar. They typically use mu for the mean of this random variable and sigma squared for the variance of this random variable. So I'm going to describe what mean and variance is right now. Okay. So this is the most basic quantity, a density function. There's also an equivalent quantity called the CDF. So we are really talking of PDFs. Okay, if you have used the name PDF and CDF. So CDF just means cumulative distribution function. Okay. Or sorry, cumulative density function, or also called the distribution function. Okay. So that notation, let me not use the notation for that because we don't really need it. I'm just saying that for every random variable, so we picked up y just to kind of describe it. So we said it's distributed according to this density function. You can also define random variables according to the cumulative distribution function, which will just say what is the probability of y less than equal to some value little y. Okay. So here it was exactly equal to, right? So for example, in the previous setting, let's say the discrete setting, we can say what is the probability that y was less than equal to 0, probability that y was less than equal to 1. I'm just using double lines here just to kind of keep it a little bit different from the other piece. And probability of y less than equal to 2. Okay. So this was the same as, I think it is 0.1. This was 0.3, so total 0.4, and this is 1, right? So it just adds up things, okay? Up to. So when I say probability of y less than equal to 1, y takes a value 0 and 1, and so you just add up those two probability values, and just write 0.4. So this has to, at one extreme it has to be 1, the other extreme it has to be 0. So yeah, I mean here it's not. I mean if you write y strictly less than 0, then it's 0. Okay. All I'm saying is there is this other quantity called CDF, or distribution function. But we'll not worry too much about this part. With random variables, the most essential element is the density function for us. Okay. And so that's okay. So is the concept clear? A random variable just is defined by a function, like a density function, which could be a probability mass function. So this discrete things are called probability mass functions, I guess PMF, and this continuous things are called density functions. Yes. Mu is here, the exponent. Yeah. A random variable is y. There is no x here. Oh no, so in this discussion we really are just isolating y and just discussing that y is a random variable, therefore it has some probability density function or mass function. We will go back to the input-output example, or basically the supervised learning task soon. I mean, in fact, right now. Any questions? Yeah.
What will be the shape of this curve? It will be a normally or
This
die-shaped
Gaussian
curve?
distribution, yeah, it's going to be a good question. So it's going to be something like this, where typically the peak is going to be at mu, and range is going to be on the x-axis is basically, on the x-axis the range is basically all the values that y can take. So it's from minus infinity to infinity. So it's really small values at really extreme. Like let's say at minus 10 or plus 10, it's really small. Let's say at mean it is what it is. You can just compute it here. Any other question? Yeah.
So you can think of PMF as taking on discrete values and then Gaussian function or
Gaussian is an example of a continuous valued random variable.
yeah, and then use Gaussians as taking out infinite values.
Yeah. So the discrete one, that's why it's called a probability mass function. You can actually write it same thing on the x-axis. You can only have, it only takes three values, 0, 1, and 2, and you can just put a, whatever, 0.1, point something, like it only takes three values, sums up to 1. So that's an example of implementation. Oh. So this is the values that y takes here. So the mean of this also you can compute actually, the discrete one. So I'm going to just define the mean and the variance. Just mean, because we only need mean. So the essential quantities that we care about are, the first essential quantity is the mean of a random variable. Okay, mean. And we'll just use y again. So expectation of y with respect to, I'm going to write explicitly the distribution. Okay, py. So y is a random variable which is associated with this distribution, this density function. Okay. So I'm just explicitly writing it. Okay. Sometimes you can omit the subscript, because if you're taking an expectation of a random variable, then you're basically just doing this. Let me write the discrete version. It's just going to be sum over all the values that y can take. So y can only take values between 0, 1, and 2 in this example, of the probability of y taking a value little y, right, times little y. Okay, it's just averaging, weighted averaging the values that y takes times the probability that the value that takes little y. So what is this? This is equal to 0.3 times 1 plus 0.6 times 2, right? I don't know how much this is. 1.5. No, it's just the y. Sorry.
Okay.
Yeah, always I'm going to use capital letters for random variables, and this is the same as before. So input output variables that I described last lecture, we're going to just call them now random variables. Okay, it's the same notation. I'm going to put bar to the top if I'm going to think of data. So now we are really not thinking about data at all. We are just introducing the notions of probability and stats, right? There is no data. So there's a random variable. It's characterized by a density function, and we're just using that to compute some other functions like expectation. Okay, so that was just a prelude to get to the first point of this section, which is let's think of a joint distribution. Okay. So I'm going to use distribution density a little bit, maybe loosely. Just think of it as something associated with a random variable. Typically, I'm thinking of the density function. Okay. Now, what is joint distribution? I'm going to use the notation p of xy for the joint density function. For I'm going to use again shorthand RV for random variable or random vectors. RVs x and y. Okay, so now I'm introducing two random variables. Okay, x and y. Then with the two random variables, there's going to be a joint distribution, a joint density function, which is going to describe the probability which they simultaneously take two different values. Okay. Let me give an example. I'm going to be a bit slow here, so if people already know this, it's fine. So let's say x and y. So let's say this is, I said x is multidimensional, p-dimensional, right? But let's, for just now, just for this, let's assume that p is equal to 1. Okay, just for simplicity, I'm just going to describe what a joint distribution is. So let p is equal to 1 for this example. Then all I'm saying is so p of pxy is just saying what is the probability that x takes a value little x and y takes a value little y. It will give me some number. So basically, for every values that x and y can take, it will give me some number, right? Let's say p is 1 and x is also x only takes values between 3 and 4, and y takes a value between 0, 1 and 2 as before. So this means, this is just a shorthand saying x takes values between 3 and 4. I mean, you can explicitly write that x takes values takes values 3 and 4, not between 3 and 4, sorry, just 3 and 4. And y takes values 0, 1 and 2. Okay. The two random variables. Okay. Then I just, for every value that, so little x and little y, just take these guys. So what is the probability that x takes value 3 and y takes value 0? There should be some number. Similarly, there should be numbers. So the total number of such assertions would be 2 times 3, 6 such assertions, or 6 such numbers you need to fill in, and they also should sum up to 1. Okay. So what I'm saying is the sum over x, sum over y of p of x takes a value little x, y takes a value little y is equal to 1. Okay. Because it's a distribution, because it's a density function. I mean, in this case, I'm using a sum notation because these are discrete. Okay. I could also, if they were continuous, I could have written integration over x, integration over y of p of x, x is equal to x, y is equal to y, dx dy, and this should be equal to 1. So join just means there's more than one random variable. Okay.
Right after the parentheses and integration.
Here, this dx and dy. It's
Oh,
just
dx dy. Sorry. Okay. Thank you.
so when you integrate, think of integration as like every small part. I'm just taking the value and it's like that. Sum them. Okay, so I wanted to introduce joint distribution because for us this it's supervised learning for the majority for the first few lectures, and that means there are two things, x and y, and so we are thinking of joint distributions all the time. So one simple thing, so there are two things that I want to kind of bring out, and it's not in the notes actually. I'm thinking on the fly here, so but it's needed for at least the first part. So first thing is, what is the probability of x is equal to, let's say, little x? Okay. Let's say this. So when I use double p, sorry, not double p, but let's say I write it this way. All I'm saying is I want to find the probability that x is equal to x when I have been given this guy, the density function. Actually, this is the same as p of x is equal to x. And this is the same as summing over y of p of x is equal to x, y is equal to y. All I'm saying is, if I want to know the probability that x takes value x, but I have been given this joint distribution, then I just need to sum over all the values that y takes, so that I only need to know what the probability of x takes a value x. Okay. This is called marginalization. Okay. Somewhere I need to write marginalization. And this is called a marginal. Okay. I mean, it's fairly intuitive. All I'm saying is, let's say x takes value 3, and let's say when x takes value 3 and y takes value 0, it's 0.1. When 3 and 1, it's 0.1, and 3 and 2 is 0.1. Then the probability that x takes value 3 is just 0.1 plus 0.1 plus 0.1. I'm just summing up 3 rows, for example. Yeah. And the second thing is factorization, okay, which I'm going to write it now. So the probability, okay, again, I'm just going to, probability that x takes a value x and y takes a value y is equal to the probability that x takes a value x given y takes a value y times the probability that y takes a value y. Okay. So this is a, which one? These one? Yeah, this is the same. I should have written subscript. I mean, so actually, what happens is people drop little x's, little y's, a lot of things. But let's see p of xy. Sorry, it's xy. Yeah, I mean, so these are probabilities. All, I mean, so all capital P's are probabilities. So whenever, okay, when I said let p, let me make it little p. So anything with extension at the top probably is little p. Yeah, that's the dimension. Ignore that one. So this is just factorization, or some of you might have seen this as Bayes rule. Okay. I mean, not yet Bayes rule, but we can make it Bayes rule. So this is just called the factorization or chain rule, maybe, of probability. It's just saying that the probability of two random variables taking two specific values is the probability that the first random variable takes a value given that the second random variable took some value times the probability that what the second random variable took. Okay. And there is no notion of first and second, right? So actually the second, so that means that I can also write it this way: is equal to probability of y takes a value y given x takes a value x times probability that x takes a value x. So this, so what might be confusing is what is this? What does it given mean? Right? So that is where a notion of, I guess, some notion of dependence between these variables makes sense. Okay. So think of, so here I said y takes three values. So let's say y takes two values and x also takes two values. In fact, let's say x and y are just coin flip outcomes. So they only take two values, 0 or 1. Let's say it's heads and tails, which I'm just calling 0 or 1. Then all I'm saying is, if you flip a coin, so let's say x represents the outcome of the first coin flip, and y represents the outcome of the second coin flip. So let's ignore 2 here. And let's say this is also 0, 1. Actually, why did I write 3, 4? Let me delete 3, 4 and just call it with that. Okay, just to keep it. Yeah, because I don't think I used those values anyway. Okay. So let's say x takes values, heads and tails, heads and tails. Okay. Instead of heads and tails, I'm representing them as numbers. Now, so x represents the outcome of the first coin flip, y represents the outcome of the second coin flip. Both are random things, so that's why x and y are random variables. Now, here we are asking what is the probability that, since I said x is the first coin flip, what is the probability that the second coin flip is equal to heads given the first coin flip is equal to heads? Let's say little y and little x are 0, 0. Then here we're just asking what is the probability that y takes a value heads given that the first random variable took the value heads. Okay. If the two coin flips are independent, then this is, given that this information, if I give you this information that this information doesn't change, the probability that y takes value heads or tails is the same as before. Okay, so this thing gets deleted. But you could have two coin flips where it's dependent. It's the same coin, so maybe flipping the first coin gives you some information about whether the second coin will land heads or tails. Like there's some dependence between these two coin flips. Okay, that's when you can kind of think of, if I give you some information about the first coin flip, it can change the probability of the second coin flip. That's the intuitive notion. If you did not this is actually just called the conditional probability distribution. Okay, conditional probability. Condition on some other event. I guess a simpler example I'll give you with a die. Actually, we are, what time is it? Okay. So we have some time. So let me give you a die-based example. Let's say, so example just to understand understanding conditional probability. Okay. Let's say x is a let's say x is a random variable which takes a value 1, 2, 3, 4, 5, and 6. So basically, it's a outcome of a dice. Okay. And y is a random variable which also depends on dice. It's basically saying whether the outcome is odd or even. It says 0 and 1. 0 represents odd outcome of dice, and even outcome of dice. Okay. Right. So what is the probability that y takes a value? Let's say it's a unbiased dice, as in like it's a nice fair dice. Then what is the probability that y takes a value 0? 1/2, right? And probability that y takes a value 1 is also 1/2. Probability that x takes value any of them, little x, is 1/6. Okay. Now, all I'm saying is the probability that x takes a value, let's say 1, given y takes a value 0. What is this probability? I've already told you it's odd out. It's odd. So this is saying I'm giving information which is that we are already looking at odd outcomes. Within odd outcomes, what is the probability that x takes a value 1? Yeah, it's 1/3. Okay. So this is dependence. So the probability that x is equal to 1 changed because you said something about y. Okay. You should look at some the review to kind of get more idea about this. Yeah. So, and very quickly, we can also, just as a bonus, we can think of Bayes rule. Okay. You must have heard Bayes rule phrase many times. It's basically just combining these two equations. Okay. So let me. So I'm going to use demonstrate some Bayes rule and shorthand. Okay. Sometimes you don't really need expansion. So all I'm saying is probability of x given y times probability of y is equal to probability of y given x times probability of x. So here I really dropped x is equal to little x, y is equal to little y, x is equal to little y, and so on. And Bayes rule is just saying probability of x given y is equal to probability of y given x times probability of x divided by probability of y. Okay. It's just saying, so in terms of interpretation, it's just saying that I had some probability of how x outcomes happen, right? Yeah, I mean, I guess this is an example of Bayes. So yeah, I mean, this is on the right hand side. You initially knew that x was 1/6. Would take values with probability 1/6 each. You can compute the probability. For each value of x, you can find the probability of y. Here I've not written it. And what is the probability of y? I think I just wrote it here. Probability of x is also written. Probability of y given x. So let's say x takes a value 1. How does it influence the probability of y? This is the easy part. I guess this is a little bit difficult to describe. But yeah, I mean, you can see that, right? So let's say x takes a value little x, 1, then probability of y is equal to 1 is 0. That is. I mean, it's not going to be even outcome if little x already took the value 1. I mean, if x already took a value, odd value, then probably that y is 0 or 1 is pretty much decided, right? So it's a very, I guess, degenerate type of a distribution which says if x is odd, then this is 1. If x is even, this is 0. It only takes zeros or ones. This problem. Anyway, don't worry about it if we can't map it to this example. All I'm saying is I just combined the two equations that we wrote before, and this is called base rule. Just for information, we probably will not use it. But we will use the notion of conditional probability. So let's come back to now our status. What is it? Supervised learning task. So we have x and y, input and output, right? Random variables now, and we want to find a function, a mapping between inputs and outputs, right? So let's see. And we had defined a scoring, a loss function rather, which scores every function that I can get. So if I specify a particular mapping from x to y, I can define a loss. And if you remember last time, it was something like f of x minus y. That's a square. Basically the square, so f is a mapping which is supposed to map x to y. It will map f, x to something. We hope that whatever it maps to, let's call it y tilde or something, it is close to y. Basically the prediction is close to y, right? And we just squared it because we don't care about whether this is less than this or greater than this. Let's say y is one dimensional. Okay. Output. We don't care about which is less than the other, but we just want these two numbers to be close to each other. Okay. We could also use, for example, an absolute value or something. F of x minus y. Okay. This is just for regression. I'm going to talk about classification, the G qualitative variable, a little bit later. So note that I have actually really used only symbols. These are all placeholders. So in capital X, capital Y is just variables, input variable, output variable. F is also a placeholder for a function, a mapping between x and y. Okay. In a sense, we can specify exactly what that function is by using data, using, I need to describe what the function is. Otherwise, I'm just saying for any function, any mapping between x to y, I can score it, how good it is predicting y in this way or this way. Okay. Yeah.
Why is the absolute value one not squared?
Because absolute value is already, it doesn't care about which one is greater or smaller than each other.
But wouldn't you get different values if you have certain numbers?
No, let's say f of x is predicting 2. For some x it's predicting 2 and your real value is 3. Then the error is, let's say, 1. Error or loss is 1 unit. If it's predicting 4, 4 minus 3 is also 1 unit. So it doesn't matter which side you're in a sense, it's always positive, first of all, if you see that these numbers are positive. So it's just saying how much is the difference between what you're predicting and what is the reality.
If the difference isn't 1, then the square root will be bigger.
Yeah, these are two different loss functions. You get to choose you as a...
Oh, they're not the same.
Yeah, they're not the same. They're not the same. They're just different examples. You choose whatever you want, and there's some reasoning to that. That's part 3. Relation to maximum likelihood estimation. But let's pick this one first, okay? Because this is the canonical one, and this is something related to residual sum of squares and least squares that we saw last lecture. Okay. And so let's say we don't have any data. Okay, we just have P of xy. Okay. The joint distribution between input and output variables. No data. Okay. Have this. Don't have data. Okay. So these two are in some sense replaceable, in the sense that if I knew the joint distribution, I don't need data. And if I have because I don't have the joint distribution, I am really relying on data. The whole notion of statistical modeling is that I don't know the joint distribution between input and output. Okay, so that's the key message. That the whole, the reason we need data is because I don't know how does X behave, like with what probabilities X takes different values, and with what probabilities Y takes different values, and with what probabilities X and Y jointly take different values. Okay, that's encoded by this object, right? Because I don't have that, I want to use data. Okay, that's the whole. That's the big key thing here. Okay, and so let's say I don't have data, then actually, given this, I can find the best, I guess, function, or this mapping between input and output. I just need this to find the best function, best in terms of some loss, some objective. How are you scoring? Why do you call a particular f best and another f not the best? So that's the criteria, and I'm going to define. Because now I have joint distribution, I can talk about something called the expected prediction error. EPE for any function f. Okay, for any function f, I can find its expected prediction error. It's like a scoring, just like I could score for any linear model last time with yi minus beta transpose xi. I can assign a score for any function f. Give me any function f, I can tell you a score, and the score definition is going to be based on this loss function defined. It's basically, I'm saying, okay, because my x and y are random variables, they can take different values simultaneously. So let me just call this the expectation of y minus f of x squared. Okay, so expectation is like this. So all I'm saying is, because x and y can take different values simultaneously, I'm just gonna average them out. In the sense, I'm gonna say, okay, this is basically maybe I can use the summation version, just for simplicity. Summation over x, summation over y. The probability of x takes value little x, y takes a value little y, times the thing over there, which is little y minus f of little x square. Okay, this whole thing is in the summation. This is the definition of expectation. Anything inside the expectation just appears as it is. Because x is taking little x and y taking little y, I just put little x and little y here. Okay, and that's the probability. Okay. You just sum over all simultaneous values that x and y can take. Okay, we just remember this. This was just the encoding of, if x was taking 2 values, y was taking 3 values, there were 6 numbers here. So there were basically 6 terms in the summation. Okay. This is just a short form for those six summations. I'm not explicitly writing all of them. And if you remember, I just told you that this joint distribution, this probability of x is equal to x, comma y is equal to y, can be written as probability of y is equal to y given x is equal to x times probability of x is equal to x. This was just, I said, just factorization. This is just true for any, like if you had 2 random variables or 3 random variables, you can always write first random variable given others, the second random variable given others, something like that. It's just called a factorization. This is true for any distribution, so we just wrote it this way. And we prefer y to be on this side for certain reason. If this is true, then I can write summation over x, p of x is equal to x, because that's the only thing which is depending on x. Summation over y, p of y is equal to y given x is equal to x, times basically the same, y minus f of x square. Okay. Basically, I pulled this term out because this doesn't depend on y, so this pull it to the left. And now let's try to understand. So this was just the definition of, this is expected prediction error. I want to find an f which minimizes this expected prediction error. So I want to find, give me some f which, I told you the joint distribution between x and y. Can you give me an f which minimizes this error? Okay, this expectation on this term here. Okay. I'm not restricting f in any way. Okay. In the sense, if you remember linear models, f of x was actually beta transpose x, some linear function. Here I'm saying I'm not going to say anything about f. Give me the best f that you can give me. Okay, and that means, so for that, let's just try to understand quickly what f of x is. So f of x is a function, right? It takes a value for every little x. Okay, so for every little x, so let's say x takes values. X takes values, what was it? Let's say 3, 4, and 5. Okay, these are only 3 values x can take. I mean, x can really take, if it's p-dimensional, it's not really 3 numbers, but let's say x takes values 3, 4, and 5. Then f of x is really just saying, is like a table, right? It's basically saying for every value that x takes, what is f of x, right? So you can actually write down a table which says takes values 3, 4, and 5. F of x can be whatever it is, let's say 1, 10, 15 or something, right? A function is just a table, right? It's a table. X takes some value, just tell me what y takes. So now, since I'm saying I don't want to restrict any f that, I don't want to restrict an f while minimizing this EPE value. So EPE score. So I want to find an f which minimizes this EPE score. And you see that in this, if I want to minimize this, okay, I want to find f of x for every x basically. Right? For every little x value, I want to find a number here such that this whole score is minimized. Right? That will give me a function, like a table like this. Find a number, find a number, find a number. Once I find all these numbers, that will be the f that will get me a score, EPE score, right? And one interesting thing to note here is that if I choose f of x to be, let's say x for x value 3, if I choose some number here, that has no bearing on any other x value. Okay. What do I mean by that? I'm just saying that the f of little x value that I assign to, let's say x is equal to 3, has nothing to do with f of x, f of little x value that I assign for x is equal to 4. In a sense, I can separately optimize for every little x. Separately figure out what f of x should be for every little x. Why is that? Right? Because this summation involves, is a summation over x, of course, little x. Maybe it takes 3, 4, 5 values. Another thing is, let's pick the value 3. So if it takes 3 values, there are 3 terms like this. Right? Let's take the first term, x is equal to little x. Let's say it's 3. So this number is fixed. Somebody gave us. This number is also fixed. This is this is the value. This is summation here. So this is also fixed in a sense. I'm summing over y could be whatever range it's values it's taking. The only thing that I can change is f of x, f little x, right? All I'm saying is that f little x, for let's say x is equal to 3, I get to change that. In the second term, I also get to change another f little x, and these two have nothing to do with each other. In the third term, there will be another f little x, and that has nothing to do with the first two, because there are no restrictions on f of x. If it was supposed to be a linear model, then they are all related. But it is not, I'm not saying anything about, you can pick any f you want, so I can define an f for every value of little x. So they have nothing to do with each other in each of the terms, okay? Each of the 3 terms in this example. And And so that means that I can actually figure out. So let's fix x to be some little x, okay? Maybe x naught, just to say that I'm picking one of the terms, okay? And I'm saying then I just need to find f of x naught, separately. In the sense, I don't care about rest of the other terms in this summation. If I can find some f of x naught, that will be the value. And similarly, I can repeat this for every term. I will get a function. Join them together, I'll get a function. Right? So what is this f of x naught? Okay, let me call it shorthand notation z. Okay, little z. Maybe I should use z. That's just for notation. I mean, I don't want to really write f of x naught. And so I'm gonna try to find this little z, which kind of brings this number close to each other. I mean, y is anyway fixed in the sense y is going over all the values that y can take anyway. So this I need to find. So I'm gonna find that by let me write the problem. So I want to minimize sum over y, probability of y is equal to y given x is equal to x of y minus z square. Okay, minimize over z basically. I just isolated one term. And how do I minimize this? You can just take the derivative and set it equal to 0. Okay, if you take the derivative of this thing, you can see that, I mean, this is a constant, okay, because there is x was actually x naught. Okay, for a fixed x naught. Right. So these numbers are fixed anyway. You had this distribution, so these numbers are fixed. So this is a term, and you want to minimize over z. So you take the derivative with respect to z of this whole thing. Okay, derivative with respect to z. What will happen is you will have the same term, p of y is equal to y given x is equal to x naught, because it's just constants. Take the derivative with respect to z, you'll get 2 times y minus z, right, times minus 1, because z has a minus 1 as a coefficient, is equal to 0. Okay, I mean, this is just saying d by dz is equal to something. I mean, that something is that. So I just put this here, took the derivative with respect to z. All I'm saying is that is this. I set it equal to 0, and then I'll get the value of z, which could either minimize or maximize. If you remember from calculus, you actually have to look at some second derivative and see whether it's minimizing or maximizing. But don't worry about it. Here we'll just we'll ignore that fact. And so if you just evaluate this, it's just going to be sum over y, p of y is equal to y given x is equal to x naught. 2 and minus 1, that's we can cancel it because it's anyway scaling, right? Times y is equal to z times sum over y, p of y is equal to y given x is equal to x naught. Okay, I just brought, first of all I deleted these two because they're just scaling. There was y minus z, so I took one term. So y was multiplying with this guy, so I left it as it is. Z was multiplying with this guy. I just brought the whole thing here, so I just copied the coefficients here. Okay, and z has nothing to do with y, so I just put the z outside. Y and y are there, so that I can't put it outside. And this is actually equal to 1, if you remember. For any given h value, if you sum over all the other guys for the second random variable, it's going to be equal to 1 because it's a conditional distribution. Okay. So this is a property. So if you have go back to the die example or the other examples that we saw earlier, you can verify this. For any fixed value of x, if you sum over the other guys, it should be equal to 1. Other random variables, all the values that it takes, it should be equal to 1. So this is 1. So basically what I'm saying is we actually got a value of z. Z is just equal to this thing on the left side. Okay, and so z is actually equal to and the left side is actually some sort of an expectation, right? It's the expectation because I'm summing over y, I'm multiplying y with some probability. It's just called conditional probability. Okay. It's still a probability because this has to, if there was no y, we just said if there was no y, it's sum to 1. So it's a density function. It's just a conditional density function. Okay. There's one additional thing here. That's why it's called conditional. Otherwise, it's just a density function. So all I'm saying is z just takes the value expectation of probability of y given x is equal to x naught. Okay, what's the right notation? Y given x is equal to x naught.
The right hand side is 1.
The right hand side, except for z is 1. Sorry, this term is 1.
Mm-hmm.
Yeah.
Then this is exactly the same.
No, there's a y here.
Yeah, but then
This y and this y, I mean, so they get one. This is like an expectation. Here there's no expectation. So think of it as this. If I sum the density function, it's 1. But I sum the density function weighted by the value of the random variable, then it's not summing to 1, right? So it's the definition of expectation. So the difference between expectation and summing a bunch of probability values to 1 is that there is a little thing there, which is the value of the random variable itself. This is the value of the random variable itself. So this is just a shorthand notation for, really not really shorthand because there's a conditional distribution here, and so to kind of capture that there is a conditional effect here, so the same thing is carried over into expectation. So this is a familiar thing that you've probably seen, I guess, without this extra stuff, right? But the extra stuff is because we said we will fix x, one of the random variables. So what I'm saying is for this x naught, for any attribution x naught, the best value that z can take to minimize this guy is this. Okay, this is the conditional expectation of y given x. Okay. Now this conditional expectation is a very conditional expectation of y given x is a very important quantity, which will let us justify the k nearest neighbor stuff that we did last time, as well as the linear model that we did last time. Okay, so it's like a unifying object with which we can reason why KNN works, why KNN doesn't work, or why linear model work or doesn't work. Okay. So if you did not understand the derivation, you can do it. Kind of pass it over offline. So we fixed for any x naught. This is the definition of z. So what happens is you can actually just write it as the best f naught. So the best f of x is just equal to expectation of y given x. Okay. What's the best notation I used? I don't know. Okay. Or what is f of best f of x is expectation of y given x is equal to x. Okay. So here I'm just not explicitly writing this, but when we explicitly write something as given another random variable, it just means that you're doing the summation over the conditional distribution rather than over the random variable itself. Okay. So y is the random variable. You're summing over all the values that y can take, given x can take some values. Like if it's little x, then given x takes little value x, sum over the conditional probability of y, like some terms like this, over y, and that's this expectation. And this is called the regression function. Okay. It's a bit confusing in the sense of why this is called a very generic name, but it is.
Just quickly explain the intuition behind why you don't need the scalars. Why you don't
These
need
scalars, these 2 and something minus 1.
Yeah, can you just explain a little more why you can just drop
because we are making this sum equal to 0, right? So, like I can multiply the whole thing with minus 2. Right hand side times minus 2, right hand times minus 1/2 is 0 still. Left hand side times minus 1/2 would kill these two guys. I mean, delete those two. Minus 2 times minus 1/2 is 1. So you can remove them. I mean, if there was any constant, let's say alpha times this whole thing equal to 0, you can delete that alpha. Okay, so we did a lot of heavy lifting, and let's take a break for 5 minutes and get back.
Some website can help to revise calculus.
Calculus we did not use much, right? Just one.
Right.
Yeah.
But like, what are the important?
Just the derivative, first derivative, first and second derivative of squared function. That's it. So which you already know, right? This is d by d z of z square is basically 2z. Right? In this case, we were doing d by dz of y minus z square. Happens to be minus 2 y minus z. Minus 2 because first of all you bring this 2 here, y minus z, and the differentiation of z with respect to itself is minus 1. So this is pretty much the rule that we used. Later on also we will use the same thing.
Okay.
Maybe just Wikipedia.
Okay.
It'll just give you these types of rules, and you just have to remember them. I mean, there is not much intuition.
Yeah.
There is intuition, but we don't need it. We just need to remember this, and it's only used to kind of get to this punchline, and we'll only interpret this punchline rather than focus on calculus. Calculus not needed.
Okay. So I don't know.
And there are some sample questions in the notes, so you can look at how the questions look like if you're concerned about exam. I have uploaded the previous lecture, re-uploaded, so there is a couple of questions there. There are some questions in this one. I'm not sure if this one has it. Yeah, there are some sample questions. If you think you don't really need calculus if you're concerned with calculus.
Okay. Also, are we supposed to have groups, right?
Yes, nobody gave me group numbers,
but I don't really know anybody here, so I don't know.
So you can message on Slack and see, and then talk to them, direct message them to see if they have good skills.
Are there other groups for two projects?
Same groups. I mean, yeah, there are groups for projects as well. You can have the same idea.
Is it like, do we have groups for assignment too, or just individual?
Both assignment and projects.
Oh, so we have like group assignments and projects.
You are welcome to do it alone, but it will be difficult. It will not be difficult. Actually, last time I offered this course, everybody did it alone.
Everybody did it alone.
Yeah, but it's. I think groups will help you kind of learn. It's better to group up with somebody who knows a little bit about this, more, let's say, so that it's helpful to you.
How many people should be in a group?
Three. Yeah. You can have two if you really don't know anybody. Then you can have two.
Okay.
Or you can do it. I mean, so people have done it alone as well. So the same assignment that I gave today, same thing people have done alone as well. It's just
we have assignment today. When is it due?
2 weeks from now.
Okay.
Yeah. Just post it on Slack. Did you say hi on Slack? Or
Yeah.
You did?
Yeah, I said hi.
Nobody said reply?
No. At least last time I checked, it didn't see it.
You said hi to whom? To general channel. And nobody said hi.
Because you said say hi on
Yeah.
Slack.
No, but I said say hi to me as well.
Oh, really?
As in, introduce yourself to me.
Oh.
But that's okay. You can introduce yourself.
That was pretty literal. I just said hi.
That's fine. So I'll make an announcement to form groups. Actually, 1 or 2 people, like maybe 6 students have formed groups of 3 each. Everybody else has not formed groups yet.
Okay, alright.
I will announce them to.
I see.
Yeah.
I don't have a group, so do you think we can make a group of 4?
4, I think, would be an overkill for this. It's last time actually every individual person did the assignments themselves. It's just the group is just so that if somebody is lagging behind, they can kind of catch up. So 4 would be too much, I think.
They don't have a group.
There are other people who don't have groups. Actually, I want to announce that. In fact, right now, people who have not formed groups for assignments or projects, this is a good time to talk to other people and form groups. Ideally, you want to be in a group where there's some complementary skills. So if you're not very, you need to brush up on calculus, maybe somebody else who has an engineering background or something may help. Yeah. 4 is, 2 is better than 4.
How many people are supposed to be in a group?
3. But if it's really exceptional, I can say 2 is fine. Even 1 is fine because last time everybody did assignments alone. Almost the same thing. But I think 1 would be, when you have the ability to kind of work in tandem and kind of split, some load, then should utilize it. Yeah. 2 or 3. 3 is preferred. Okay, let's resume. Sorry for the short break. I think I spent too much time on background to get started on the 4 goals that we had today. Also, these notes, I'm going to post these notes, so you don't really have to try to repeat whatever I've written here. I should have said this at the beginning. Only last time, because the projector did not work, I wrote it on the board. Otherwise, I generally share these notes, along with the lectures. So you don't have to write the same thing, but if there's something I said that you think is important, then maybe you want to scribble it down. Okay. So we did a lot of, the first part you might think why the hell did we derive this? Why did we care about EPE and why did we kind of say this object is interesting for us? Is because, let's say you are not in the data world, you only had the joint distribution between x and y. Without data, you can say what is the best prediction function. The prediction function is going to be for every x, find this conditional distribution of y given x. So this is just a function of your joint distribution. If you had the joint distribution table, let's say for every xy value, what is the probability? You can find this because this has a summation form. If you see, a little bit above, I had written some summation form. So what I'm saying is, if you just had a joint distribution, this is the best function in terms of the squared loss that we wrote earlier. So f of x minus y squared. If you want to minimize that on average with respect to the joint distribution, then this is the best prediction of y given x. Okay? This is the prediction of y given x. Okay? This is one number per x. Okay. And now we are going to talk about, that was when we knew the joint distribution. The whole, all these methods that you come across, random forest, that you've heard of, is because we don't have the joint distribution. And so we have to talk about data and create a function f, another function f, using just data. And KNN does that. And last time we said KNN just does, it basically says f of x, let's say f, I don't want to write f itself, so let me call it fknn maybe, just to kind of say that this is a specific function. And this was just 1 by, I guess k, sum over xi in the neighborhood of x, or x. I mean x naught. Let's say, it doesn't matter. I mean some fixed x naught that was given to you. You have data, so you just pick all those data points which are in the neighborhood of x naught and take the average of the y's corresponding to those xi's, right? Remember, this was KNN. Or in terms of, I mean, just pictures, as I said, in 2 dimensions, let's say x naught was this, okay? That was somebody asked you what's the prediction for this point. You had your data set, which is like some x's here, okay, all over the place. Maybe you were looking at, let's say k is 3, then you're just asking, why is there 2 dots here? Oh, okay, this x naught. Let's say this is x naught, the circular one. Let's say k is 3. Then you just look at the 3 closest, I guess, x's. Let me just make it further away. Yeah, maybe these are the 3 closest x's. Okay. So you're just asking for what are the 3 nearest guys. Maybe these 3 are the nearest guys. Actually, this is a very lopsided picture. Let me just change this. So let's say this is a circle. We're looking at, okay, in the neighborhood, which are the 3 closest points? Let's say k is 3. Just looking at the y values and just averaging. Okay. That's what KNN does. And now the interpretation is that, you know, you have this best prediction function, expectation of y, given x is equal to x. What is this really? This is just saying, you know, it's basically saying, okay, well, let me write the definition. Sum over p of y is equal to y given x is equal to x times y. Okay, sum over y, whatever values y say. Okay, so imagine a situation where, you know, I'm asking for prediction at x naught. Okay, what if you had at that x naught, so x naught was also there in your training data, so you ask for prediction at x naught. There are, you know, x naughts in your training data as well. So in the sense x naught comma some y, x naught comma some y. In a sense, you ask for an x naught, and on x naught I have observations in my training data, and there are many observations. Okay, which means there are different y's potentially. Then this averaging is same as this averaging. Okay. Why is that? Because this is saying find an expectation of something, right? At x is equal to any fixed x. At x naught, if I had observations, those observations are like the empirical. I mean, so this averaging is like the empirical averaging of this expectation. So I guess the simpler, just to kind of say something about just expectation. If you had expectation of x, some expectation of some random variable z, okay, then a way to approximate this is just to say 1 by, let's say I had n observations of z, then it's just 1 by n sum over I is equal to 1 to n of little zi. So if I had a random variable, all I'm saying is I had n observations of this random variable, like realization, then an approximation to the expectation is just an average of my data. This is not clear? Yeah. Yeah, we'll get to the neighborhood part later. Yeah, this is for the 2 levels of approximation. Yeah, so this is the definition of KNN, by the way. This is what the actual KNN does. We are trying to motivate why this may be related to this conditional expectation of y given x naught. And there are 2 approximations. I'm trying to explain the first one, but let's hold on to your question for 1 minute. I will come back to this neighborhood business soon. What I'm saying is, first of all, this is a simple fact that if you have a random variable, okay, and you're talking about the expectation of the random variable, then it's somewhat, you know, if you don't know the distribution, but you have data of, you know, in the sense there's sampling of these random variables, then you can just take the average of these realized numbers, right? Like for example, okay, I can give an example, but I'll lose some time. But so let's say z is a random variable which is like the heads and tails. You know, it's just a coin flip. Okay, z takes value 0 or 1. Okay. Okay. And the coin is unbiased, as in it's a fair coin. So the probability that z takes a value 0 is the same as probability that z takes a value 1. Okay. The expectation of z happens to be 0 times, 1/2 times 0 plus 1/2 times 1, which is going to be 1/2. Right. So the right hand side is 1/2. If you did not have the, if you did not know that it's, with 1/2 probability 0 or 1, you flip the coin, 100 times, and you see, maybe the first time it landed a 0, second time it landed a 1, and so on. You just add those numbers. Maybe 55 times it landed ones, as in maybe tails, and 45 times it landed heads, as in zeros. Then 55 divided by 100 would be your approximation to that 1/2. Okay? I mean, 55 divided by 100 is not exactly 1/2, but it's like close to 1/2. So expectations can be approximated using data. So that's the connection. And this was derived not using data. And we are saying that if you had data exactly at this point you had observations in your training data, then you can say this expectation I can approximate by my data, some averaging of the data. But what is the chance that in your data set you would have multiple observations at the same query point that you have? Okay, it's very little. So you do a second level of approximation, saying that at the exact x0 I will probably not have any observations in my data. So let me spread out, look at a neighborhood, and look at some what data sets did I have in my neighborhood, what data points do I have in my neighborhood, and then average them. Okay. So that's this averaging. So that's two levels of approximation. One is the approximation of the expectation itself, and the second one is there will not be any data point exactly at that x0. So let me kind of look at a neighborhood of x0 so that there will be some data points, and then that I can average.
So is there a method when we use the expectation method? Is there a scenario when we use the expectation method or
No.
the neighborhood method?
No, so this is not a method, right? This is like a conceptual understanding. So this is like backing why KNN is principled. So here, last time I just wrote, okay, just average the enough points in a data set. And it's like, okay, you can also define random other things, right? Unreasonable heuristic things. But this has reasoning that this is actually approximating this in some way, and therefore it makes sense. Okay. So that's the principled, thinking that you need. So if you come up with new methods, hopefully they're approximating this in some way, or are trying to say something about this in some way. Okay, and we'll see linear regression also says something about this in some way. So that answers your question. Yeah.
So is it going to be true in both cases of discrete and continuous variable, or this approximation is better for continuous variable? Or
yeah, I've been using so this is a data set is anyway summation, but this definition of a conditional expectation may not be the summation. It can be continuous variables. It can be an integration here. So yeah, so for us it will not matter whether the joint distribution is a continuous density function or a discrete density function. Pretty much, unless you go into the theory of statistics, then there will be some issues potentially. Yeah. Is that clear why KNN makes sense? It's basically two approximations. Okay, and where is this? 2. So linear model are directly saying that the conditional expectation of y, let me assume, this is an approximation, conditional expectation of y given x is equal to x, let me assume that this is actually equal to beta transpose x. Okay, it's like saying, I don't know what the joint distribution between x and y is, the pxy, which is kind of, if I know pxy, I told you I can compute this, but I'm going to assume that this conditional expectation of y given x is actually linear. That's like a strong restriction assumption. I'm not willing to look at any other conditional expectations. I want to say that this is actually equal to beta transpose x. Okay. This is an assumption that I want to make. Okay. Here it's really not making an assumption. Here it's saying that I can, I don't want to assume anything about this, but I will approximate this using data, this empirical averaging business. Okay. Linear models will say, I want to assume something about this. Let me not think about data at this point. Let me say that this conditional expectation is actually a linear function. Okay. So that's the relation between this conditional expectation, this is regression function, to approximations that the first method and the second method are making. So linear regression is kind of it's a very simple thing. It's just saying I just want to assume that this is equal to this. I mean, so you may ask, like, why is that assumption needed? Well, it's not. Okay, let's see. Yeah, I mean, if you make this assumption, so assumes this, and because of this, because I assume this, I can actually compute what the best, what the best model is. Okay, let me not put hat here. Okay. Best beta just happens to be equal to the expectation of x transpose, not the matrices. Okay, these are the random variables themselves, inverse expectation of x times y. Okay, and I mean, so one thing is if you assume that a function is now related across instances. If you remember EP definition, we said they are unrelated, so we solved per x what the z was. But here we are saying they are all related across x. There's this relation relating parameter beta. So it turns out that if you now minimize the original EPE with respect to beta and get the best beta, this happens to be this. So this is again not dependent on data. These are random variables. These are random variables. There's expectation over, like here only x's appear, so it's expectation over p of x. Here x and y appear, so here it's an expectation of p of x and y. Okay. Other thing is, this is the closed form expression, and this is very similar to the closed form expression that we did I write last time? I'm not sure, but there is this closed form expression for beta hat using least squares or residual sum of squares, which was x transpose x inverse x transpose y. Okay, this is data. The bars here kind of say that this is data. This is not nothing to do with distribution. This is something to do with distribution only, nothing to do with data. You'll see that these forms are kind of similar. It just, you kind of removed expectations, and you took in the fact that it's a matrices, so that's why some transpose is going somewhere else, but because they are two different things anyway. But you can see that the form is the same, right? Expectations is gone here, and this is a matrix of observations. It's the transpose is slightly different. Okay. Just to dimensionality, But what I'm saying is, linear models assume this about the best guy, and this is without the data, this is with the data. So we'll actually kind of revisit the interpretation for linear models soon. I mean, we'll actually potentially try to derive this. It's again just uses one property in calculus. The second derivative, like rate of change of the second derivative, of some function like z square is 2 times z, something like that. That's the only fact we use from calculus. We'll try to get to that towards the end. But before that, let me just talk about qualitative variables as well. Okay. The qualitative variable will give us something called the base classifier. Okay. So there were two things to do, kind of get to this conditional expectation of y given x is equal to x, right? One was the loss function. I used square loss, and I just said I want to minimize the expected square loss. That was the EP definition. For qualitative variable, I need to define a loss function. So the loss function is going to be, I'm going to describe it using a matrix, okay, which is going to be let's say I have 3 classes, okay, dog, cat, and fox. Okay, it's a qualitative variable. So let's say input is an image or some features of the animal, and I want to say it's a dog or a cat or a fox. Okay, so just and so maybe when so I'm drawing a 3x3 matrix because there are 3 classes, and on the on one side I'm going to say what was the truth and what did you predict. Okay, so if the truth is cat and you predicted cat, I'm not going to penalize you, as in I'm going to set the loss to be 0. In the sense you're fine. If truth is dog and you also said dog, it's fine. If the truth is fox, you also said fox, it's fine. I'm just trying to encode how would I say you're bad, right? Maybe, and so this, let's say this is truth, okay, cat, dog, fox, and same thing. Predict. This side is predicted, and that side is true. So all I'm saying is, okay, it doesn't matter, but okay. So if, let's say you predicted dog, but if the truth is a cat, then maybe you want to kind of say it's not such a good classifier, classification model that you put in. So here you want to potentially say loss value of, I'm going to penalize you or score you that you're doing bad by saying you're off. And same thing over here. I can put any numbers there. So maybe 2 here, maybe 3 here. Okay, maybe not. Yeah, I mean, so I can put any numbers here. I can keep it symmetric. I can keep it asymmetric. 4, 5, 6. Doesn't matter. Okay, this is a way to describe loss. In the regression case, I just said the loss was just a square, basically y minus f of x squared, right? Here, it's a quantitative variable. Let's call it g, and let's call the prediction function g hat. Okay. So it's a prediction function. So it actually has to take a value x and spit out a prediction. That prediction either is the same as g, so the truth is cat and the prediction is also cat, or the truth is cat and my prediction is dog or fox. If it's dog or fox, I need to penalize it, so I need to define a loss function. Here there is, we were said if the truth is 2 units and my prediction is 3 units or 4 units, then this is my loss. For every value that y and f of x take, I can define what the loss is, the difference between these two squared. Here, g only takes 3 values, three values or 3 labels, cat, dog, and fox. But g hat should also take 3 values, cat, dog, and fox. And so there are only 9 different combinations of what was the truth, what was the prediction. Okay, so that's I'm just writing this way. And here I'm saying there is no loss for if you predict correctly, and there's going to be some loss if you get prediction correct. And these numbers you get to choose, you design. And so there's going to be an EPE, okay, for any prediction function okay, I think in the notes I've used some not so nice notation. So let me call this function g, prediction function as g. Okay, I don't want to put a hat because hats are generally you think of it in terms of data. So in the notes I've used hat for that small part. So let's not worry about hat. So let's say my prediction function is g. Okay, here it's just very synonymous to f. F is, let's say, continuous. For quantitative variable, g is for qualitative. Just similar thing. So EP for any prediction function g is going to be same thing as before. So sum over x of p of x is equal to x, and sum over, instead of y, there is going to be values that g takes. So let's say g takes the value. So let's say cat is 0, dog is 1. Okay, let me just not put 0, 1. So let's say cat is 1, dog is 2, and fox is 3. Okay, just numerical values associated with, just numbers associated with the 3 classes or 3 labels. Okay, so I'm gonna say okay, sum over little k is equal to 1 to 3. I mean, in this particular example, the probability that my prediction function is equal to the class k, right, given x is equal to little x. Oh, sorry, this is so this is actually the random variable the random variable g takes 3 values, right? This is just I mean, I'm just writing the EP value, so I just okay, I still have one other multiplication left, which is multiply times the loss. Okay, this is the loss of g takes the value k, comma, your prediction g of x. Okay. So the only thing that changed from before is this was squared loss from before, this thing, this was y minus f of x squared, remember, from a page ago, and this is the same as before. I mean instead of g is equal to x, there was y is equal to little y. There's really no difference between what's written here and what was before. And same as before, we can say we can just say minimize just the term inside for fix x to be x0, fix x0, and we can just minimize the sum over k is equal to, let's say, 1 to 3, p of g is equal to k, given x is equal to x, times the loss of g is equal to k, and I think last time I used value z. Okay, minimize over z. Right? I mean, if, just like before, the values, I mean, since I don't restrict my classifier, yeah.
What's the digit on the left there, that last line?
Here?
On the left. I think it's a dx by 91.
Fix x0, minimize over z.
Sorry.
Yeah, sorry, this is fix x0, I mean, same as before. Minimize over, I mean, I could have put z here or some g of x0 here, directly, it doesn't matter. I'm just saying, just copy this term inside and you want to minimize that. And you can just eyeball and say when, so this loss is just saying, so z is my prediction, right? It can only take 3 values in this example. This one, this one, this one. And loss is saying, loss can also, the g itself can also take 3 values, the variable itself. Okay? And so this is just a lookup. This is saying if g is equal to k and you are predicting k prime, if g is 0 and you're predicting 0, then this value is 0. If g is 0, you're predicting 1, this value is 1. So how do you minimize this? Okay, you minimize this by actually setting z to be actually equal to k. Yeah, so the way to minimize this quantity is to set z actually equal to k. Right? When you set z is equal to k, so okay, first of all, this is summation over k. So which k will you set is the critical thinking here. In a sense, what I'm saying is, for every k, ideally you want to set z to be equal to that k. Then this loss value is 0 because it's in between here, right? But here, since there is a summation, you want to set this to be one of the k's such that this number, this is as small as possible.
How come you don't set it equal to 0?
Z equal to 0. Yeah, z can only take 3 values. There are only 3 values in this example that you can set z.
Why can't you set the whole thing to
Okay. The last time what we did was not set this itself equal to 0. We said take the derivative with respect to z and set it equal to 0. Take the first derivative with respect to
You
z.
can't do that for this.
We can't do that, I guess, because this is not a continuous function. Loss is like it's just shifting. Z is not continuous actually. Z is only taking 3 values.
Right. Gotcha.
And since z is only 3 values, you just want to minimize this. Let's see. What is the question? Yeah.
That summation is over that whole line, right?
Yeah, the summation is over from here to here.
Okay.
Yeah. Yeah. Otherwise, you would have just said this is equal to 1 or something. Right. I'm seeing if there's an easy way to say the solution. That's all. So I'm thinking on the fly. Okay. So you're going to set that z which maximizes, okay, the solution is, for this problem, is that you're going to set that z which maximizes these probabilities. So for every z there are 3 numbers here, right? For z is equal to, so the k only takes 3 values, so there are 3 such numbers here, right? The 3 numbers here. So if we set the z corresponding to that k, which has this number to be the highest, okay, that's going to make this whole summation the smallest. That's a little bit of, I guess this is a long sentence. All I'm saying is, I want to figure out how to pick z, and my only, I guess, choices are z is equal to 1, 0, 1 or 2. I'm going to choose z is equal to one of them, for which this number is going to be the highest. For that z for which this number is the highest, if I choose that z, okay, yeah, that terms, for that k, this term is going to be 0. Okay. So the intention to minimize loss is to just pick that z for which this number is the highest. I guess I'm not sure. Some of you are lost here. Actually, how many of you are lost for the past 30 minutes? Okay. We can go slow and kind of. That's why you should ask questions. And also, this is a a learning environment, so you really have to ask questions. There's no question which is outside the scope or down one. Yeah.
When you are explaining, we understand, but we cannot visualize it.
It'll take time. It'll take time. So you don't expect that you learn. It's not like undergrad. Undergrad, you just listen, go to the class with A's and get an A. Okay. You just listen and it'll be in your memory. Here, it'll take time to decompress and go through the material. But the thing is, the nice benefit is by the end of the semester, you'll be like, you can recognize between somebody who's actually taken a training in data science versus somebody who's just using buzzwords, right? And you want to be on the latter side. Yeah, so there were several questions. Yes? Okay. There were mostly, I guess, people are pointing out that they were not following, but yeah.
So in this
Questions?
case, the z would be 3 according to the
So depends on x naught, right? So we fixed an x naught. All I'm saying is we want to minimize this number, right?
So
And the only way is the only way this number is gets high value is because loss is non-zero and there's a corresponding multiplier here. These numbers are non-zero. So you want to kind of, to minimize this, you want to try to set z to be the same as this, for which this is the high number. So if this is a high number and you don't set z to be that k, then this value is not going to be 0, and so you will incur a high loss. Okay. Actually, I should point out what I'm saying. Let me actually not point out, actually change it. So let me change this. Or some constant, okay? It doesn't matter. Okay. for symmetric and nice loss matrix. It's just saying every time you make incorrect, whether you are incorrectly saying, instead of cat, incorrectly you're saying dog or fox, I'll just penalize you the same value. For this, I guess the interpretation is fine, right? It's just saying, if you say something incorrect, these are the numbers which will add to your loss or score, right? So basically, if you're incorrect, there will be one of the numbers will be highest, and that number will fall into, will kind of come into your score. So you want to kill that highest number. That's the only way to minimize the score. I mean, you can kind of reason it for for this example by exclusively writing it out and seeing. So there are only three choices. You can substitute all three choices and see when is the score the lowest. Even abstractly this way, and you figure out that the z that should be equal to that k for which this number is the highest. And okay, so this only makes sense for this loss. I should write it explicitly. This symmetric example, there's zeros and some non-zero numbers on the off diagonal. Okay, and that is so basically what I'm saying is, let's call that particular function g. Okay, that particular function, let me not use g. G was a symbol for any function, any classifier. So that function is called max over. I'm not going to give a name for it. There's a name in the notes, but little k is equal to 1 to capital K. That's the k classes, 3 classes, for example, of the probability that g is equal to little k, given x is equal to x. Okay. So this is the equivalent of that conditional expectation of y given x is equal to x. Actually, there should be argmax. So there's some error in the notes. Okay, anyway. So this prediction function, so for classification, what we are saying is, if we had the joint distribution between g and x, just like y and x before, all we're saying is the best classifier is just going to classify at any given x point. Just tell me what is the probability that g takes value, 1, g takes value 2, g takes value 3. There will be such numbers, many such numbers. I'm going to assign that class for which this number is the highest. That's kind of very intuitive, right? It's just saying at any given point, there's the conditional probability that label can be cat, label can be dog, label can be fox. If we knew the true joint distribution between joint distribution g and x, just take that conditional probability. Just take that label for which that conditional probability is highest. In this previous example, there are only 3 conditional probabilities for any given x value, like an image of a cat. The conditional probability that the outcome is a cat probably is the highest, right? So you just choose cat, rather than the conditional probability that given an image of cat, the probability that it's going to be fox or dog is probably lower. So it's a very intuitive classifier actually. It's just that it comes out as a way, because we define EP like this and we use this loss matrix. Any big questions? Any foundational questions? Like maybe not understanding the second order things like the notation I'm using. You'll get used to it soon. Yeah.
I will double check. Right to the left of max, you added something.
Oh, good question. This is argmax. It's just that index which maximizes this number. Because I want to make a prediction, right? So I need to either say 1 or 2 or 3 in the previous case. This is just a number. It's going to say, yeah. It's just a shorthand that you'll see in the books, for example, both the books. Okay. This is called, I guess this is called Bayes classifier. And in the notes there is a nice diagram of I think it's a 2-dimensional data set with x2 and x1, and I think there were a bunch of one side was orange and the other side was blue colors. Okay, here I'm just in terms of diagram, I'm just putting x's. And the base classifier will be base classifier's decision boundary. So remember, decision boundary was the one where you're not sure whether, in fact I'll define the decision boundary to be those regions of the input space, this is two-dimensional space, where the conditional probability that G is equal to, so in this case there are two classes, the conditional probability that G is equal to 1 is the same as the conditional probability of G is equal to 0. So find x's, so there will be some region here such that, some points here for which the probability that it's G is equal to 0 is the same as probability of G is equal to 1. Let's say x's represent one class and zeros represent the other class. So this is data, but what I'm saying is there's this some region here, and that's the region I guess drawn like this. Where there are some circles here as well. So this is called this is the decision boundary and corresponding to the base classifier, where it's saying that on this line the probability that the true probability, this is the Disjoint distribution between x and y is, it's derived from that, right? This is the conditional probability of G is equal to k given x is equal to x. Happens to be the same. So you're not sure which class this point x belongs to in these two dimensions. Okay. And that's why it's called a decision boundary. So basically on decision boundary you're not sure what should be the class. Okay. Because there is no single argmax, in the sense there is no single k for which this number is the highest. For both k's, in this case there are only two k values, 0 or 1, or 1 or 2, such that for both they are the same value. So remember last time I guess there was a decision boundary for linear classifiers, linear methods, which was like something like this, straight line. So here there is no straight line. So ideally, without data, no data, if we need the joint distribution between G and X, this is what we want. We want this base classifier, and we want, and this would be the decision boundary. This is the best in terms of the loss function that I defined. If you're correct, there's 0 penalty. If you're off, there's 1 penalty or a constant penalty. Any questions about decision boundaries? Yeah.
So the decision boundaries is where all classes are equally likely?
Yes. Yeah, equally likely is the way of saying that probability of G is equal to 0 given x is equal to x is the same as probability of G is equal to 1 given x is equal to x. The two probabilities are the same, equally likely. Two conditional probabilities are the same. Yeah.
So is K and N for continuous and basis for classification?
Good question. Base classifier is the best classifier for classification. Regression function that I defined, the conditional expectation of y given x, is the best regression model for regression. So KNN is one technique. It's approximating the regression function. Here we haven't really said what approximates this base classifier. So this is not data driven, right? This is not based on data. This is just saying if I need the joint distribution, I can find this conditional distribution. I guess the equivalent thing to this guy, this star, is that EP, this guy, this guy. So for classification, for regression, no data. If I had the joint distribution between x and y, then this is the best prediction according to square laws. Okay. This is one scalar. So for a given x, I can find this expectation over my, using my conditional distribution of y given x, I can find this expectation that will predict some number. That's the best prediction. Okay, for the squared laws. Similarly, this guy is the best prediction for a class. If I know the joint distribution between G and X, I can find the conditional distribution and I can make the best prediction for a class. Okay, this is the best classifier. It just uses the joint distribution between G and X. And there are methods which will approximate this. this guy. Just like linear regression was approximating the conditional expectation of y given x as some linear function. Here, later on, I think 2 classes from now, we'll see something called logistic regression and something called linear discriminant analysis or whatever. So those guys approximate this guy. Those methods, those techniques will approximate this. Just like KNN and linear models are approximating that conditional expectation of y given x. So 2 best things we have already computed. The rest of the lectures are all about how do you approximate these guys. I think it will take some time to kind of map it, and if you're not sure, let's discuss right after the class as well. Any other questions? Okay. How much time do we have? Half an hour. Okay. So let's get to the second part, which is why KNN is not enough. Okay. Actually, KNN, I said it's a technique for regression. It can also be used for classification. I guess that's where maybe your confusion is, that KNN can also be used for classification, where how would you use KNN for classification? You would say my prediction, so G hat KNN for a given point, let's say x naught, would be, instead of an average, it will just say take the majority of GIs such that xi is neighbor of x naught. Okay, this is a very bad notation, but all I'm saying is a neighbor k neighbor of x naught. All I'm saying is it's the same thing. So given an x naught, KNN is a lazy classifier, right? It doesn't do anything actually. Given an x naught, look up my data and find all the xi's which are close to x naught, k guys, k xi's, right? Look at the corresponding class labels. Now these are not y's, but these are like cat, fox, cat, let's say there k is 5, cat, fox, dog. Then take the majority, of what those labels are saying. 3 are saying cat, 1 is saying fox, 1 is saying dog. Then your prediction is just cat. Okay. Instead of taking average, if these are numbers, you will take average. If these are not numbers, these are numbers, but they have an interpretation in terms of labels. Because it's a classification task, you just take the majority vote. Okay. Yeah. So, in case of? In case of tie, you can decide what to do. You can flip a coin and pick one. Yeah, these are, like this definition has an issue, as you pointed out. Yeah. You need to figure out something. Some tie breaking. Yeah, that's one fix. You can take k as odd number, but then the number of classes need not be just 2, right? So yeah, you just pick k. That's one way to break ties. You can do other things. It's fine. Okay. So this is not the reason why k is not enough. That's for classification. So the reason it is not enough is because this neighborhood is problematic in when p is large. So what is p? Sorry, p is the dimension of input variable. Okay. When the input variable is like there are only like x1 and x2, there were only 2 dimensions. If I had 1000 dimensions, I can't even draw them anyway. Maybe I can draw pairwise. Then I'll have 1000. Choose 2 plots, I guess. Too many plots. So when p is large, the notion of neighborhood doesn't make much sense. Okay, that's what breaks KNN. You can't really understand who's neighbor of who in a 1000-dimensional space. Who's neighbor of who in a 2-dimensional space? You can just eyeball, plot and eyeball, and maybe somebody is a neighbor of somebody else. But in 1000 dimensions, you can't figure that out. Okay, and I'm just gonna. explain that using a simple example, which is let's say let's think of a cube. Okay, let's think of a unit cube, and I wanna say, so this is in 3 dimensions. Okay, and similarly you can have a unit cube in 2 dimensions. It's going to be a square like this, right? Unit cube just means 0, 0, 1, 1, and then 1, 0 here, and 0, 1, right? I want to say I want to capture 10% of the volume of this cube, or there are 2 cubes here, so 10% of volume of each of the cube. Okay, why is 10% of the volume? Let's say my data is spread uniformly in this on this cube. Okay, just for simplicity, just for intuition, let's say my data is spread out in this cube. I want to capture 10% of the volume, because if I capture 10% of the volume, I'll have 10% of the data, right? Because data is spread out uniformly. So what is the 10% volume? Let's say the top left corner is what I want to capture. Okay, then basically I know that 10% is 0.1. Let's say 10% is 0.1 is equal to length square. I want to find the side length of this box, which captures 10% of the volume. This is the 10% of the volume. Let me shade it. Okay. Right. Side length, that's it captures. So this is somehow the neighborhood. Okay. Definition of a neighborhood. I mean, in a sense, I'm just saying that there's a volume, and this is the side length of the region that captures that volume. And you can imagine, okay, it's only considering capturing 10% of the volume, so it's a reasonable notion of a neighborhood. Right? So L is whatever, square root of 0.1. Okay. You can do the same with cubes. Then it's going to be 0.1 is equal to L cube, right? And so on. And so in general, it's going to be, let's say, so in 100 dimensions, it's going to be L to the power 100 is equal to 0.1. Okay, and it so happens that or 1000 dimensions, whatever, it so happens that the choice of L, which will give me 10% of the volume, the value of L actually goes to 1 as you increase dimensions. In the sense that there's some L which is square root of 0.1. I don't know what that value is actually. There is a plot in the. Let me just guess this. Let's say it's I don't know how much is square root of 0.1. I don't know. So what I'm saying is the 1000th root of 0.1 happens to be close to 1. Okay, which means that to capture 10% of the volume, the side length I'm looking at is pretty much the full, almost the range of each coordinate of my input variables. So it's like if my input variable is one is age and one is let's say household income. It's like I'm taking the age from almost 0 to 99 and taking the household income from 0 to a million or something to get 10% of the volume region. Like to get a small neighborhood, I'm really like looking at really huge individual input variable coordinates. So that's bad, right? That means how is a million close to $10, or how is the other coordinate high upper range close to the lower range. So that breaks the notion of neighborhood, right? They're not close to each other. Do you understand what I'm saying? Or another way to look at it is if you fix, let's say you call the neighborhood to be exactly that neighborhood for which each xi is only like plus or minus small number from some mean value, from some fixed number, then that captures increasingly really small volume as you go up in dimension. So maybe in 2-dimensional, it's for this small range, it's capturing 10%. For this range in 1000 dimension, is going to capture like very minuscule amount of volume, which means that almost no data point will fall in that volume. So that means, which means there is no neighbor. Okay. So the neighborhood notion has an issue for KNN. And so that's the whole reason why we are looking at linear models, nonlinear models, even neural networks, all this stuff. Okay. Okay. So I don't have too much to say about this dimensionality issue, in the sense, because the notion of neighborhood breaks down, you want to kind of look at other models. That's the summary here. Okay, so now let's look at linear models. 3 and 4 I'm just combining. Okay, 3 and 4 bullet points that I started at the beginning of the class. Linear methods or models. Okay, and so what is linear model? It's basically saying y is equal to beta transpose x. No, not y is equal to beta transpose x, but f of x. This is the linear assumption, right? I'm gonna so one thing that comes up in some other courses, and you might have seen this, is that x is the input variable. You can actually kind of transform it to a different x, in the sense you can. So one example is, let's say this is x is two-dimensional, x1 and x2. Okay, I mean one realization of x happens to be little x1, little. Okay, maybe not. Okay, this is not the right notation. Let's see, x1 and x2. Okay, I put superscript because I'm using x little subscript as observation. Okay. So all I'm saying is, if you had this, you can always do something like x1 square root of x1. x2 minus 5 x1 times x2 and so on. Okay, in a sense, I had some features, some measurements like household income and age. I can take square root of age, it's positive, so it's okay. I can take household income minus some value. Okay. I can multiply age and household income. So these are just called, I guess, interaction terms. So basically, it's like feature engineering. You had some raw measurements. You're saying, okay, I don't want to look at these. I want to look at these guys. That's perfectly okay. Okay. You don't have to do it, but these are things that people do. Okay. And I'm just saying that this is also, I'll just call it x, because I don't want to say, like, you can call this raw variables, and these are like transformed variables. The reason why I brought this up is because, just because somebody gave you measurements, the linear model doesn't mean you only exactly have to say it's beta 1 times 1 of the inputs and beta 2 times other input and so on. Okay. You can always do these types of multiplications and so on, and then say my prediction is going to be linear in these guys, right? So that makes, actually, you can have nonlinear functions of individual measurements, or even pairs of measurements, and still have linear coefficients to them. Okay, so linear models are really not restrictive. Okay. Okay. So this was the model choice, and there was this notion of residual sum of squares. I think last time I just introduced what this is. This was just a sum over. If I have data now, so I is equal to 1 to n observations, yi minus beta transpose xi squared, right? For any model beta, so now because it's linear models, all models are parameterized by any beta value, like the coefficients that I give for the linear expansion, right? So for everything, for every beta, I can score that beta by using my data this way. Right? I can assign a score. I mean, I can also normalize it 1 by n, doesn't matter, it's constant. This is called residual sum of squares. or least squares. By least squares, I guess least square solution is the solution for this. Okay. And I want to draw two connections, and that's where 3 and 4 is. And the 3 part would be that it's related to assumption. Related to maximum likelihood setup. Related to a maximum likelihood setup. And I'll tell you what maximum likelihood is. And 4 part is just saying how is that beta hat is equal to some matrix transpose X inverse matrix transpose Y. Okay, this is again data. Don't forget that I'm putting bars here, so don't confuse this with this X. So those are the two things. Yeah, the relation to maximum likelihood setup, and I'm gonna kind of revisit maximum likelihood I think 5 lectures from now. So here I just want to say residual sum of squares, the choice of this loss function seems arbitrary, but once there's a way to interpret it which makes some people happy, and it's going to be as follows. We're going to say, remember we were thinking of joint distribution between x and y, right? First thing is, let's say x is not random. Okay. Which means, okay, first thing is, let's say x is not random, and let's say y is a function of x in this way. Actually, is a function of x with some noise, in the sense of with some randomness, where epsilon happens to be what is the choice? Can you see that? Okay, epsilon happens to be, let's say 1. I mean, it doesn't matter. Let me put 1 for simplicity. So whenever I said there is a joint distribution between x and y, okay, extensions of that. One extension is you can say y is just a deterministic function of x. So x is random, y happens to be x squared or sum of x's, individual x's. That means that y is not random anymore. Given x, y is just a deterministic function of x. You can do that. Here I am saying let's not make x random, but y random, by saying that y is a function of x with some, but another random variable is being added, and therefore y is random. So this random variable is epsilon. Epsilon is normally distributed, so it's like a value. Remember epsilon was something which could take values between minus infinity to infinity, right? All I'm saying is, given an x, the way y gets generated is that given an x, you do beta transpose x for some beta. Beta is also given. And then you add an epsilon, you draw a number from this normal distribution, you add that to this number, and that would be your realization of y. So of course, for the same x, you can have different realizations of y, because I can get different numbers here. Okay, so y is random. This is some assumption that I'm making. Okay. Under this assumption, okay, there's this notion of maximizing likelihood. Okay. Likelihood. So here, since x is not random, I really don't want to work with this because there's nothing like that. So I'm going to work with p of y given x. Okay, because x is not random, so x is fixed. So only randomness is y. So there's going to be an object related to y, and the method of the principle of maximum likelihood says that so there's a parameter here beta. Okay, so just like before, I'm just saying that X is not random. There exists, there is some beta for which, y just gets added with some beta transpose x plus some thing which is actually random. And I know the distribution. This is normal. Okay, with exactly mean 0 and variance 1. That means that P of y is equal to little y given x is equal to little x is actually equal to 1 by square root 2 pi e to the power minus little y minus beta transpose little x square by 2. Okay. Why is this true? Because y is just a shifted. It's like saying I have this normal random variable, x is given, so this whole thing is a constant for any fixed beta, which means that y is also a normal random variable, but with this as a mean. Okay, that's all. It's like I have a normal random variable, I'm putting a constant, adding a constant, which means that normal random variable instead of mean 0 will have a different mean. Okay, and that means that the conditional distribution of y, which is now random variable because it's right hand side as a random variable, it takes different values. In fact, values from minus infinity to infinity, and it takes values according to this condition, with this probability. Okay. This is just a definition of normal distribution, except I just I could have written probability of epsilon is equal to little epsilon. Forget about x; it doesn't depend on x. To be the same thing, except epsilon minus 0 because it's 0 mean, right? Is this confusing? Clear? Okay. Yeah.
In the normal distribution definition, for the 2 pi, you had a
Sigma.
sigma.
Yeah, very good observation. Here I chose sigma to be 1. Good. So there is a sigma and there is also a sigma square here for one-dimensional distribution. We remove that. It's just, we can put that in. So this is the probability of y is equal to y is equal to y given x is equal to x. Now we have data which is yi comma xi, right? I is equal to 1 to n. Maximizing likelihood just means maximize. So first we'll write probability of y is equal to little yi given x is equal to little xi. Okay, that I can find out because I have this data xi yi here. I can just put in yi here, xi here, and find this number for that particular xi yi, right? Right. Except I didn't specify what beta is. So I still can't compute this number. If I told you a beta, you can compute this number. So this is actually, so I can compute this number. I'm gonna just do a okay. I'll take the log of this number. Okay, I haven't still specified beta. I take the log because there is a exponent here, and this is anyway constant, so you can ignore this constant. There's an exponent here, so exponent and log hopefully get cancelled. So I'll take this log, okay, and I'll do a summation over all I is equal to 1 to n. Okay, because I have n observations, I can compute these numbers for every observation, provided I told you what beta is, right? Like if I told you some beta, you can completely evaluate this number, this summation of n numbers, right? Now this thing is called the log likelihood. Okay. Without the log part, this is called the likelihood of the data xi y i. I added the log part. That's why it's called log likelihood, and the summation is because I have n observations. That's all. This is called the log likelihood, and typically people also people think of it in terms of maximizing the log likelihood, maximizing the, let's call it log likelihood LL as a function of beta. Okay. Since I did not specify beta, now tell me what beta should I choose such that this log likelihood is the highest. Okay. I have used my data, so for any given beta, I can find what this number is, right? And I can do that. I add those numbers up for all n observations. Now I'm saying, can you find me a beta such that the likelihood of the data is the highest? That's the interpretation. Okay. And and you can just substitute. So I just wrote down the definition of, so this thing I just wrote down over there. If you take the log, what happens is there's a negative sign, so you maximize over beta, take the log of the exponent, ignore the 1 by root pi, so you'll get minus yi minus beta transpose xi square, and there's also divided by 2, I guess, right? And there is a summation over I is equal to 1 to n, is there, right? The same thing, as the summation is here, log of something, I ignored this because this doesn't have beta at all, some coefficient. So exponent and log cancels, and there's a minus of yi minus beta transpose xi. 2 also you can actually ignore, to be honest. Now this is the same as, is actually proportional to this very bad symbol like this, I guess, is proportional to minimization over beta of the sum of I is equal to 1 to n of yi minus beta transpose xi square. A maximization of a negative quantity is the same as minimizing a positive quantity. That's why I put a proportionality. Basically, I'm trying to delete this one. And I can also delete 2 because it doesn't affect choice of beta. Now this is actually just residual sum of squares. This is residual sum of squares, right? This is the residual sum of squares. So I guess what I'm trying to say is there's a route to get to justifying residual sum of squares by saying I'm going to assume something about my data, that y is equal to x plus x transpose beta plus epsilon, kind of say that this is the conditional distribution of my output given input, and because this is the conditional distribution, I'm trying to maximize log likelihood, and that will give me some expression like this, and this happens to be residual sum of squares. So there's a way to justify why you're doing residual sum of squares. Okay, that was the point of this part. Otherwise, y square term, like why did we prefer square versus, you could have chosen absolute value. Okay, that could be justified if there was a density, if there was some distribution which would have an absolute value here potentially. Okay, Gaussian has the square value, so that's why we make a Gaussian assumption. You can justify the choice of the square thing. Okay, in the last 7 minutes, we can derive y beta hat, which minimizes, so beta hat is the one which minimizes this thing here, right, is equal to data, I'm writing it so many times, okay, y. I'm not sure if I have time to do that actually. Okay, so residual sum of squares, that was I guess RSS, this thing, can also be written in a vector form. Okay, that's the first observation, is equal to y matrix minus x matrix beta transpose y matrix minus x matrix times beta. Okay, this is the first observation, that sum over here can be written as this transpose this, and it's not really too complicated. It's actually just this. I'm going to write it explicitly so that you can visualize why it is true. This y matrix minus x transpose beta is actually, each row happens to be yi minus let's call it, I guess, beta transpose xi. Okay, y1 x1 yi minus beta transpose xi. Okay, here it's y1 minus beta transpose x1. Yeah, I guess last one is yn minus beta transpose xn. So actually this one you can see, so y is n dimensional, n rows and 1 column. This is n rows and t columns. this is p rows and one column. So this whole thing is n rows and one column. Okay. This is a long vector. It's basically a tall vector with n rows and one column. And each row or each element of that vector is this, just yi minus beta transpose xi. The first one is y1 minus beta transpose x1. Ith one is yi minus beta transpose xi, and last one is going to be yn minus beta transpose xi.
Beta transpose in this one column? Or
Yeah, I could have taken x1 transpose beta. It's the same. Beta transpose x1 is the same as x1 transpose beta. You're asking here?
Yeah.
Yeah, this ideally you would have written x1 transpose beta. Yeah.
That doesn't matter, but by looking at beta over there, I was thinking to be the trans.
Here?
Yeah.
No. Dimensions. So this is n times p.
Uh-huh.
This is p times 1.
Yeah.
Betas are, I mean, all my vectors are always column vectors. Okay. N times p times 1, that's why this is the n times 1. This is n times 1. That's why I can do vector summation element wise, and that happens to be this vector y1 to yn minus each individual, this n dimensional vector, which is beta transpose x1, beta transpose xi, and so on. All I'm saying is this is the same as this, and this guy's transpose is this, right? So first element is the same, second element is going to be here, last element is going to be this guy. Okay. And now if you multiply this, a vector transpose a vector, okay, is going to be this times this, plus second term times second term, last term times last term. That's just that. Okay. This is the definition of inner product. I mean, the only reason why I define this vector, representation for residual sum of squares. By the way, this evaluates the scalar, as in a single number, is because I wanted to illustrate how to get to beta hat using these matrices and vectors. Of course, you can always try to take the first derivative of this with respect to beta, like beta is p-dimensional. You can take the first derivative with respect to beta 1, set it to 0. The first derivative with respect to beta 2, set it to 0. You can find that and then figure out what beta has to be. And it turned out, because if you do it that way, you will have lots of summations, lots of individual data points here. Xi, x1, x2, x3, x4, y1, y2, y3, y4. It's hard. Yeah, I guess you'll get to the same answer. It's not in a nice clean way. Here, the only reason I wrote it in this form is because here you can actually very easily get to this form. Relatively. It's just a little bit of calculation needed. And because I have 1 minute, I'll show one part which is easy. Which is, this can be written as, by the way, if there is an expression like this, if there is a transpose of two things, you can just break it into minus beta transpose x transpose, x theta transpose. Okay, I just brought the transpose inside. Okay, and AB transpose is B transpose A transpose. There is some elementary linear algebra. I think I gave you guys some review to look at, right? That has that identity, and this is y minus x beta. This is equal to, now you just do multiplication. This times this times this, and 4 times. You get 4 times. Y transpose y minus y transpose x beta minus beta transpose x transpose y. Oops, I have one more term. Okay, plus beta transpose x transpose x beta. Right? 4 terms. Okay. First term doesn't depend on beta. Anyway, the next 2 terms depend on beta in a linear way. Okay. It's like something times beta. So this is like a vector. This eventually this happens to be a row vector. Okay. Row vector times beta transpose times another row vector. Okay. What I'm saying is these 2 terms resemble something like A transpose beta. Something like that. This term resembles something like beta transpose some matrix A beta. Okay. The matrix being X transpose X. I'm just replacing them by simpler symbols so that let's not get confused. So all I'm saying is now I can say d by d beta of A transpose beta happens to be equal to A, which is p dimensional. Okay. This is the first thing that we can derive, and the second thing is d by d beta of beta transpose A beta happens to be A plus A transpose beta. Okay. And we will try to derive it next class or something like that. All I'm saying is why am I writing this, right? I mean, you probably already know calculus, except I'm writing these because this is vector calculus, vector derivative. Beta is a vector, p-dimensional. I'm saying that p-dimensional. So this is a scalar value, A transpose beta. Its derivative with respect to vector is a vector, which is also p-dimensional, and that happens to be A itself. So if you have a function of a vector beta, which is like A transpose beta, then its derivative with respect to the vector beta is A itself. This is easy to see. Right after the class, I will show it to you, some of you guys. This one is not very easy to see. This just requires some algebraic computation, but this is a quadratic function of beta in the sense that there will be beta square stuff here. And for that, if you take the vector derivative of a number with respect to vector beta, and it has squaring kind of stuff, then it happens to be still has a function of beta. It's like A plus A transpose times beta. So you can imagine. So if let's say this was let's say beta was scalar, A beta. So d by dB of A beta is just A. Remember, one-dimensional thing. And here, this is A beta square. If beta was a scalar, right? Then that would be A plus A times beta, which would be 2A beta. So if there's a beta square, there'll be 2 factor coming in, and that's captured by this matrix. But you can think if this was the same matrix, then there'll be a factor of 2. So you would see that. Okay. That's it for the class, official class. The first part I'll just show it very simply. It's very simple. We'll break. Yeah. I'll post the notes, okay? So don't worry about writing notes in the class. Like, try to understand and ask questions. Expressions didn't make sense. So remember previously when k nearest neighbor, we just said this part is the same. Find all the points which are nearest to my any given x naught. So let's say you give me x naught, I'll find the point close to x naught. Previously I said take the average of all the y values corresponding to x height. Here I'm saying collect those, instead of y's, these are qualitative variables. So collect those gi's. You can't just average them because averaging doesn't make any sense, because one could be representing cat, one could be representing fox. The average of cat and fox doesn't make sense. Just take the majority vote. Just see how many GIs correspond to cat, how many GIs correspond to fox, how many GIs correspond to dog. Whichever is the highest number, it's like saying how many said cat, 3 said cat, how many said dog, 1 said dog, how many said fox, 1 said fox. Therefore, since 3 was the highest vote for the cat guy, so you predict cat. That's it. It's like majority vote. Yeah, no average. It's called majority vote. It's like voting. I have these K guys. 3 of them are saying cat, 2 of them are saying dog, 1 of them is saying fox, and I just say cat.
You think it's decision boundaries
Not decision boundary itself.
well, when there's a line, like a linear line going through
Between two classes.
that's essentially the minimization of regression. It's kind of like
But that is not, that's the minimization of RSS. So in 2 dimensions, you have class 1 here, class 2 here. There is a decision boundary, but that boundary corresponds to that boundary corresponds to beta 1 x1 plus beta 2 x2 is equal to some constant.
Yeah.
So beta 1 and beta 2 are the ones which minimize RSS. Like the beta is just beta 1 and beta 2. So you find this beta using the RSS stuff that I talked about last lecture and this lecture. But once you find the beta, this line, which is the decision boundary, is actually this is equal to a constant. Otherwise, it's not a line.
Yeah, so in the 2-dimension, you can think of that as like a line.
A line.
A line of best fit.
No, this is not the line of best fit. This is the line where you are confused. You're confused. So if you get a point x here, you're not sure whether it's in the positive class or the negative class. So decision boundaries don't make sense for regression directly.
I think I'm thinking of regression. I think I'm thinking.
Oh,
of
regression.
Like the line is closest to all the points.
Oh, regression. I mean, 2 dimensions. You'll have to think of imagine a plane, but in 1 dimension, right? I mean, regression you get other points. Yeah. So this is going to be beta 1 x1 plus beta 2. So this is y. This is x1. So some offset. This is the line. Equation of the line. So this is the line. Yeah.
So the decision boundary line isn't like.
This is only for classification. Only for classification.
So it's not the line that's closest to the points. It's just going through the 2 boundaries, right? It's just going through the.
For classification, it's the confusion boundary. For classification, let's say in 2 classes, that line decision boundary is saying I'm confused about one class or the other.
So when you say confusion, you don't know which class you're in.
Yeah. So on this, so let's say this is class G is equal to 0, and this class G is equal to 1. This is just saying the probability of G is equal to 0 given x is equal to x on this is the same as probability of G is equal to 1 given x is equal to x. So at this point, the conditional probability of class being 0 is the same as the conditional probability of class being 1. So you're not sure which class it is. So it only makes sense for classification. Decision boundaries don't exist for regression. But last time we used the regression with a threshold for classification. So that's why we got a decision boundary.
Sorry, guys.
In lecture 1 notes, in the lecture 1 notes, there was a statement mentioned for the k-earnest model, like the effective number of parameter is n by k. Now, the one thing is what is parameter in this case and how it is like n by k.
So I didn't explain that in the class at all. But for nearest neighbors, today, for example, we saw it's basically averaging neighbors, right?
Yeah.
So it's basically saying if you had n data points, okay, because I'm roughly averaging k neighbors, like I'm averaging k neighbors, not roughly, sorry, averaging k neighbors. So you can think of me having n by k neighborhoods. This is all for intuition. Effective parameters and all that is my intuition. If I had n data points, n observations.
Okay.
If I'm grouping together k guys,
Okay.
I can think of roughly that there are n by k neighborhoods, which is a leap of faith actually, but still.
k neighborhoods.
Yeah, because I have k guys in one neighborhood.
Fine.
I have n points, n by k neighborhoods.
Okay. So
And in each neighborhood you are taking an average. It's like a number per neighborhood, and that's why I have n by k roughly numbers to compute, and that's why it's called n by k is effective dimension.
so basically parameters are the neighborhoods.
Yeah, number of neighborhoods
Number
is
of
essentially
neighborhoods.
1 parameter per neighborhood, which is the average of that neighborhood.
Okay.
But the effective parameters, I'm not going to ask about anything related to that.
No, actually that was a statement which I was confused.
Yeah.
The one example that you gave here.
Yeah.
So this is the example only for cats, right? That if
True value is cat. What you're predicting is cat, then you score it to be good, right? Which means it's 0. There is no error.
Okay, so the 3 values that you said for z.
Yeah, the summation is when g is equal to k is equal to 1, g is equal to 1, it's cat, g is equal to 2 is dog, g is equal to 3 is fox. Right?
Okay, so this will become maximum if we take only the cat case when z will be equal to 1.
Oh, you're trying to understand the base classifier. So first of all, these numbers need not be ones, okay? If they were not ones, you don't have an interpretation.
Yeah.
I mean, you don't have this base classifier interpretation. You can always do that. But if you had these as ones or constants, then the interpretation is, so you are anyway, there are 3 terms here, right, for each of the class. G is equal to cat, G is equal to dog, G is equal to fox. And there will be probability values here. and there will be loss value. The loss value, so let's say you picked cat. So for a given x, the true value is actually cat. Okay, in the sense that probability is the highest.
Right.
When for a given x, if I say the true value is cat, that means that the probability that g is equal to cat is higher than probability that g is equal to fox or g is equal to dog. Okay. Since that probability is high, if I make a mistake there, that probability times the mistake, which is 1 unit, will get added on to my loss. So
this will
I'm
be,
trying to minimize that. So that's why
will
I'm.
be 0 if all if this matrix would have been 0 0 0 for cat. Then
No.
the
That
loss
should be
value.
1, right?
No, this matrix is fixed. We're not changing the matrix.
Okay.
We are just choosing. So here we are only choosing. We only have a choice of z. Okay. If I change the z, right?
So that will be the expected values, right? That won't be the true values.
No, z is one number I can choose. Z 1, 2, or 3. Cat, fox, or dog. Sorry,
Right.
cat, fox, or
Any
dog.
of it,
Okay.
Yeah.
Let's say I fixed cat.
Yeah, cat.
I still have 3 terms here. Okay. Then I'll choose. I predicted cat, and there will be a cat term here. That loss will be 0.
Yeah.
But there will be 2 other terms. Will be
Two
cat.
other terms.
That loss will be 1s.
Right.
But there will be corresponding non-zero numbers. These guys. That will be the score for me predicting cat. Right. But we know that if the true for that x, if the true value was cat itself, then I have eliminated the highest probability. Like out of the 3 terms, the term which was the highest number was the one.
Will have the loss 0.
Yeah, which has lost 0, so that term got cancelled out because I predicted cat.
Correct. Value.
Yeah, I don't know if you understood what I said.
Predicted cat means the number of observation of cat in the observation are more than compared to fox and.
No. If I given x, so basically there's a probability of g is equal to cat, given x is equal to x, times the loss of loss of cat, comma your prediction z. Right? There are 3 terms like this. Probability of I guess fox given x is equal to x times loss of fox and what you said plus probability of dog given x is equal to x times loss of dog comma z. Right? There are 3 terms like this. All I'm saying is you get to choose z. Let's say in this case probability of cat given x is equal to x is greater than probability of dog given x is equal to x and greater than probability of fox given x is equal to x. And all I'm saying is that for this case, this has a higher probability. One of them has to be higher probability, right? I mean, there's another case where numbers can be same. Some numbers can be same, but let's say in this situation there are 3 numbers. One of them, let's say one number is higher than the other 2 numbers.
So you're eliminating
In this situation, the question is, I have 3 choices of z. Which z should I pick so as to keep the summation lowest? Okay. If I pick z to be cat, this term is 0. So I lose this number. I lose the biggest number, which means my remaining numbers are just sum of these 2. But if I don't choose z to be cat, I'll have sum of these 2 or sum of these 2, which will still be higher than the sum of these 2. So my only choice is to choose cat to keep this number. Yeah. And the choice of cat is basically because, so the choice of cat was encoded in base classifier as saying pick that z for which these numbers are the maximum. So if you remember base classifier, it was basically max over k is equal to 1 to k of t of g is equal to k given x is equal to x. Basically it's saying pick this thing.
But why did you say that you can minimize? Okay, this is just minimizing z, right?
Yeah, minimizing this number.
Okay, and
Minimizing
then
over
how
z.
will take the maximum of the probability for the base.
If you want to minimize this, the choice of z happens to be the one, actually it's R max. I mean that k for which this number is the maximum.
So from
This is the choice of z. I'm saying that this choice of z will give you the lowest number here.
so ideally this part of the equation must be maximum and this will be
No, if you choose these, only these numbers become zeros or ones, right? So just understand from, don't worry about like looking at abstracting like this. There are 3 terms. If you choose these, one of them will become 0, the other 2 will become 1. If you choose cat, let's assume this is true. Okay. For this, you have to choose this. Otherwise, if you choose z to be cat, then this number is gone, the biggest number is gone, then you are only left with 2 other numbers because these are ones. Okay? But if you don't choose cat, this number will remain. And irrespective of whichever number you pick, that number is going to be smaller, that number is going to be larger than the sum of these two numbers. Like if both sides add one of the number, one of these smaller numbers, that still is going to be larger than, that number is still going to be larger than the sum of these two. What I'm saying is the sum of these two is always the smallest. In this setting. Sum of these two is smaller than sum of these two, sum of these two is smaller than sum of these two. And those are only 3 choices. If I take one of these, I'm summing these two, which is these two, or I'm summing these two, or I'm summing these two. And I said this is the largest number, so I should never sum this guy. And to not sum this guy, I need to pick z to be cat. And that interpretation of picking z to cat is basically this. Pick the cat, pick cat because cat is the one which maximizes this. Out of the 3 numbers, cat is the one which is maximizing this.
So through here,
I guess it's not very intuitive, huh?
So from here we are getting here, right? So we have to first identify which one to pick, and then we have to go here and pick.
This is just a nice encoding to say. So here we already figured out, right, what to pick.
Yeah.
And the choice of picking, we just neatly wrote it down as this. Yeah. I mean, you can in English you can say pick the z which maximizes the conditional probability of dependent. What is this qualitative variable given x is equal to x.
Thank you.
I think all these things are pretty fine. We'll come.
You want data? Then,
yeah, like
then,
how
then
to
I would
use
say
it,
drop this class and go to 572.
No, we are in 572.
Then drop this class. Data is there in assignments. Open the assignment, do it. You'll get data.
Professor,
Thing is, these concepts are not generalizable across data. I mean, you can, but by even initializing the data and understanding the data and then coming out and then again seeing some other data where this same thing is for takes time. So that's why we just generally talk about directly this.
Professor,
If that's your question, why are we not looking at examples? Right?
Yeah, because that makes I think.
I already gave the example of cat, dog, and fox. Right? I mean, beyond that, it's kind of difficult. I mean, I can show some tables and things in R, but yeah, we'll see.
Because it becomes more understandable comprehension because if you get to do ourselves that particular thing, the whole thing by us. That's what I find.
No, but you get lost in that data specific detail. You should not assume that only for that data some pattern holds. Right? This is a pattern which is a general principle.
So basically, based on the data, we are figuring out which pattern is best for us, whether linear model or KNS.
That you will do. Yeah, we haven't discussed that, but yeah.
So that is the main broader picture of what we are going to achieve.
Yeah. I mean, you are doing probably the same thing in 572. Some of the things, like KNN, probably you are seeing same thing there. I'm sure.
we haven't started with KNN yet.
So you will. So that's why if you take 572 and 575, then you'll get the data examples part there. And we have assignments where you really have to understand this to do the assignment. So, and they are data intensive. I mean, in the sense you work with data.
So like there was one place where we learned that if we don't have a data and if we know the joint probability,
then you don't need basically data science is because I don't know the joint distribution, I have to do all this exercises. If I had the joint distribution, I know what the best solutions are. I just wrote them down, right? That's it. Then the class is done. And the whole issue is that we don't know these distributions. And again, at the beginning of the class, I said this notion of distribution is also fake. In a sense, we are thinking that there could be a distribution which generates data. It may not be true. Like a physical law, I was telling you, if you flip a coin, initial condition and the dynamics of the wind pressure and the amount of force that you apply and all that will keep the it's a deterministic system. It's Newtonian, governed by Newtonian mechanics, right? Newtonian physics. But then we assume it's random. It lands heads with some probability, tails with some probability. So first of all, statistics and probabilities itself is an approximation. But within that approximation, if you knew the joint distribution, you didn't have to do all this cross-validation and data-driven stuff, because if the joint distribution is given, you know the solutions of whatever thing you want to come up with.
it's not given, so you have data to approximate the distributions roughly, or basically approximate distributions like KNN or linear models.
And Professor, do we have the lab session today?
Today is what day? No, but what is the date? No, today actually the room is booked by somebody else or something. That's why we couldn't reserve the room. Yeah, I think from next time there will be.
And lab session will focus on what things?
He will probably work with R.
Okay, but using
He will show how to use R functions and do some data analysis. It will be more compute intensive. He will tie it, of course, with the stuff you see in lectures. Yeah.
Would that be after class or some other day?
No, it's from 1 to 2, right?
Okay.
On Saturdays, select Saturdays. So he will announce, or he is supposed to announce.
But not today. He said
If he has not announced.
He said that from starting from 3rd of February.
Yeah, if he has not announced that, yeah, from 3rd of February.
It's there in Slack.
Yeah.
Thank you, Professor.
Thank you.
Oh, you have a class right now?
Oh, we just have an event at 1 o'clock. I'm drafting
Oh,
up
okay.
some things.
Okay.
Open house for graduate school.
Okay.